Greetings to everyone. Now we are going to see working of PN diode. First, let's see the formation of the PN diode, and then later we'll go in detail how it works as a PN diode. So the formation of PN diode is simply nothing but we'll take intrinsic material or pure silicon material in which on one side we will diffuse with the acceptor impurities, we call it as P region. On the other side, we will take uh, donor impurities and will diffuse. So that region is called N region. Now let us look at immediately after forming the PN junction. What are the things that are going to take place in the PN junction, nearer the junction, where the meeting point of P and N regions. So as you can see here, the electrons from N side will be diffusing towards the P side. The process is called diffusion because the N side is highly doped region for electrons, and P side is not doped with the pentavalent impurities. Of course, minority carriers will be there, electrons, but it is very less in concentration. So that is why normally diffusion takes place from high density region to low density region. So here high density region for electrons is the N region. So that is why electrons will be moving into the P region. Holes can also move from P region to N region. So in consequence, what is going to happen is the electron which crosses the junction may recombine with the hole. So that electron hole pair get disappeared, leaving positive immobile ion on N side and negative immobile ion on P side. So that nearer the junction we will be having the region which is not having any free carriers. You call it as depletion region, which offers the potential difference, as you can see, which you call it as barrier potential. So that is how PN junction is formed. So as you can see, the detailed procedure here. And here, if you see the potential barrier, that is about 0.7 volts in case of silicon diode. If it is a germanium diode, it will be around 0.2 or 0.3 volts. So if you see the circuit symbol, you can see like this, where anode on the left side, cathode on the right side. Okay. So as you can see here, this is anode and this is cathode. So this arrowhead indicates the current direction. Okay. So wherever we want to use the diode in the circuits, we are going to use this as a circuit element. Next. So now after forming the PN junction diode, we have to make it conduct if it is required. So to make it conduct, what we have to do is we have to bias it. So how we can bias is we have P region and N region, right? So as you can see here, P region must be connected with positive terminal of the DC voltage, and N region must be connected with negative terminal of the DC voltage. So biasing is nothing but applying DC voltage with the suitable polarities to the PN junction diode. So that is called forward bias of the junction diode. Now let's see, after forming the junction, how the carriers will move in the junction diode. So that is called working. So as you can see here, in N region, we'll have majority carriers, electrons, and on P region, we will have majority carriers, holes. So in between, we have the free carriers, sorry, space charge region, or the region which doesn't contain any free carrier. So which offers the potential barrier. So if you see now, as you can see here, the electrons are starting from the negative terminal of the battery, moving into the N region, crossing the junction, and then after crossing the junction, each electron will move in the valence band from hole to hole, and then leaves the p side as electron and reaches to the positive terminal, completing one closed circuit. So that is why now the diode is said to be conducting. Okay. So this is how we can make the diode forward bias. And if you want to make the diode forward bias, if it is a silicon diode, minimum voltage needs to be applied is 0.7 volts. If it is germanium, 0.3 minimum voltage is to be used. So if you see the features, it behaves as a low valued resistor. So the current is mainly due to majority carriers. So the current is large in case of a forward bias. So here it behaves as a low valued resistor, and then the current is mainly due to the movement of large number of carriers. You call it as majority carriers. And here the depletion layer width will be reduced in case of the junction diode is forward biased. Okay. Now let us see how we can make the diode reverse bias. So what is that you have to do is you have to connect negative terminal of the battery to the P region, as you can see here, and positive terminal to the N region, so that this is said to be the diode is connected in reverse bias. So now let's see how the diode works in reverse bias case. So as you can see here, negative terminal is connected to the P region. It attracts the holes, so holes will be moving away from the junction. Okay, and electrons on N side will also be moving away from the junction. Why? Because here the positive terminal is connected to N region. As you can see the movement, see here. So the holes are moving towards the negative terminal of the battery. Electrons are moving away from the battery, which causes the depletion layer width increases, and hence potential barrier also increases. So here no majority carrier can cross the junction, and hence the current is very minimum or negligible amount of current. That current is also due to the crossing of minority carriers the junction. So electrons from P region and holes from N region crosses the junction, which constitute the current, which you call it as minority current, and that current is independent of the reverse voltage that is being applied. It is due to the minority carriers that are mainly depends on the temperature or ambient temperature. Okay, so this is how exactly it explains. So as you can see here, few whole electron pairs are created due to thermal hesitation, minority carriers you call it as. Small current flows across the junction called as reverse saturation current. So that current is almost fairly constant independent of the applied voltage. If you keep on increasing the voltage, so after certain period, after certain amount of the voltage, the junction is going to be break. So after breakdown, once again, large amount of current flows through the diode, which is unintentional, and we should not operate the normal junction diode after the breakdown. So this is the current component diagram, where you can see the current ratios. So here if you see the N region, you have electrons are majority carriers, so large amount of current that is due to the electrons, and there may be minimum current due to holes. So on P side, we have large number of holes, so majority current is holes, and less current is due to electrons. So in total, always the current is going to be constant. So the total current would always be the summation of the hole current and electrons current. Okay, on either side. So now let us look at the characteristics on forward bias. You can see this, the curve where up to the cut-in voltage, you are going to get zero current. Thereafter, it increases exponentially. In reverse bias, reverse saturation current is almost constant before breakdown. That is called reverse saturation current. So as you can see the curve where the current is increasing exponentially after the cut-in voltage. So somewhere here the cut-in voltage, thereafter it is increasing exponentially. And in reverse bias, it is constant, which is equal to IO, reverse saturation current. After breakdown, there is a large rupture of the junction, so that's why large amount of current flows through it. This is the current equation, I equals to I1 to e power V by eta Vt minus 1, where V is the applied voltage, IO is reverse saturation current, Vt is volt equivalent of temperature, which is T by 11,600. Eta equals to 1 for germanium and 2 for silicon. So this is some pictures of the junction diode where the cathode is indicated with the band. So as you can see here, this is the band which indicates cathode. On opposite side you have anode. So this is anode and this is cathode. So that's how we will be indicating the terminals of the diode when you are doing any experiment. Applications, if you see, the AC-DC conversion, over voltage protection, clampers, limiters, voltage doublers, signal detector in AM FM receiver, transistor bias compensation networks, digital logic. Thank you.